Well, the camera froze, so I'm picking up from here. I had to do a little whiteout error, but 3.59 moles. I now have the number of moles of all 4 elements that are present in this sample. See how I said it's going to build from the stuff last week? We are building. What we need to do here, okay, step 3. We're going to turn it into a ratio. So we're going to divide all of the molar values by the lowest. So we're going to identify which element has the lowest amount of moles in this sample, and we're going to divide all of them by that value. So if I compare sodium, hydrogen, carbon, and oxygen, it's by a narrow margin, but carbon has the lowest number of moles. So I'm going to divide all of them by 1.17 moles. So this gives us the ratio. Sodium, I've got 1.19 mole divided by 1.17 moles. And that gives me 1.02. Mole and mole cancel each other out. There's no longer a unit. And I'm going to round this now, guys. Okay? So that's a 1. I'm going to repeat for hydrogen. Why am I rounding? Because I'm looking for a ratio here. All right, if a ratio of 1.02 to 1.03 is essentially 1 to 1. Carbon, this one is going to be exact. 1.17 divided by 1.17 gives me 1. I'm going to write that again just so it's all in the same line here. And finally, oxygen, 3.59 moles divided by 1.17 moles gives me 3.07, which I'm going to round to 3. Now I see that the ratio of sodium to hydrogen to carbon to oxygen is 1 to 1 to 1 to 3. And I can write that out as a chemical formula. I'm going to add one step here. I got lucky. Here they are all whole numbers. If they are not all whole numbers, you're going to multiply by a factor to have whole numbers. Or divide. You'll have to figure that out. So, for example, maybe you multiply everything by 2. Think back to us balancing combustion reactions. Remember when we had 1.5 oxygens? And I just said, well, multiply everything by 2? Same thing here. Maybe you saw that you could divide everything by 1.5 and give you whole numbers. That will make more sense when you see that problem. Finally, we use the ratios to write the empirical formula. So that gives us, we have 1 sodium, 1 hydrogen, 1 carbon, and 3 oxygen. For funsies, press pause and name this. So that's either sodium hydrogen carbonate or sodium bicarbonate, also known as baking soda. Next time you're baking, if you put a teaspoon of baking soda in something, you know that that teaspoon is 57.4% oxygen by mass. These are the things that you've wondered that you finally get to have answered in chemistry class. Let's try a sample again. Okay, so here's an example. I'm going to write it out. You are going to press pause. You're going to try it. All right, and then compare to me. I'm just going to work through it here. The example is determine the empirical formula of a compound that's 50.91% zinc, 16.04% phosphorus, and 33.15% oxygen. We're going to remember that this is a 100.000 gram sample. So that tells me that the mass of zinc is going to be 50.91 grams. The mass of phosphorus is going to be 16.04 grams. You guys should have already paused by this point, by the way, to write it out. And the mass of oxygen is 33.15 grams. Step 2 is to find the number of moles of each. Okay, so I take the mass of zinc and I divide it by the molar mass from the periodic table, which is 65.39 grams per mole, which gives me 0.7786 moles. My sig digs are all intact and I have the number of moles of each element in this unknown compound. So my next step is to identify which has the lowest amount of moles when I compare these three, and I see that it is phosphorus. Okay, right here, this is our lowest. So that means I'm going to divide all of them by 0.5179 moles. And that's going to give us our ratio, okay, of elements in this compound. Here I see that's 1.503. We're going to come back to that one. That's what we get. Right here, 1.503. That's not, a 100th or 1,000th off of a whole number. But remember that step 4 on the last page where I said multiply it by a factor or divide them all by a factor. So here, could I divide it by 1.5? That's not going to give me a whole number. If I multiply this by 2 though, whatever I do to 1, I have to do to them all right now. So that gives me 3, 2, and 8. Look at those whole numbers. So that means that I have 3 zincs, 2 phosphoruses, and 8 oxygens. We've never seen a compound like that, right? If you, though, look for polyatomic ions, we know that PO4 is a phosphate ion. So I'd recognize that I should probably write it like ZN3PO4 2. There's that one. This is so fun. I love this. I love this chemistry, guys. I love it so much. Let's try another one. Press pause, write this out, and find the solution. Determine the empirical formula for a compound containing 69.88 grams of iron and 30.12 grams of oxygen. Okay, I've given you the masses. It's not percentage. We don't have to go and say assume 100 grams. So I'm just going to get right into it. The mass of iron is 69.88 grams. Mass of oxygen is 30.12 grams. Let's find the number of moles. Molar mass of iron is 55.85 grams per mole. Okay, here are our two values, our two molar values of each element. 1.251 moles of iron, 1.883 moles of oxygen. Which one of these will we divide by to get our ratio? Correct. Iron. Iron is the lowest. You start a new page. So I'm going to divide. Start this again, 1.883 moles. I'm going to divide both of them by the lowest value, which is 1.251 moles. That gives me slight pause, guys. Yes.
Good day.
Thank you. You too.
Bye.
Bye. Well, sorry for that slight pause, guys. There was an unexpected delivery. Okay, so that gives me 1 and 1.883 divided by 1.251 gives me 1.505. These are not whole numbers. I'm going to multiply them both by 2. 0.5 multiplied by 2 gives me a whole number. So that's 2, and that's 3. That leaves me with the formula of Fe2O3. We're done. We're done an empirical formula. We're not done the rest. So we need to remember empirical formula does not necessarily equal the molecular formula. This is especially true in molecular compounds. Okay, so what do we need to have to go from empirical to molecular formulas? We need to have the actual molar mass of the compound. Okay, let's move on to our last set of problems. This is a long one, I'm sorry guys. A long note. So for example, the empirical formula of a compound, we've determined it for you. Okay, it's determined to be B, that's a 3, BH3. Okay, what do we know? We know that it's a ratio of 1 boron to 3 hydrogen atoms in this compound. We also know that the molar mass is approximately, we used one of our lesser than scales in the lab, 28 grams. So I want to know what is the molecular formula. Okay, step 1, we're going to find the molar mass of the empirical formula. So for BH3, That would be 3 times the molar mass of boron, 1 times the molar mass of boron, plus 3 times the molar mass of hydrogen. Okay, that's going to give us 13.84 grams per mole. That's the molar mass of this compound. It does not match the molar mass of this unknown compound. So we know that the empirical and the molecular formula are not going to be the same. We are going to divide the molar mass of the molecular formula by the molar mass of the empirical formula to determine our scale factor. Which I'm just going to call X. Okay, so X is molar molecular mass divided by the molar empirical mass. So 28 grams divided by 13.84. These are grams per mole. These are molar masses. And that gives me approximately 2. So our scale number is 2. That means that we take our scale factor, multiply it by our empirical formula, which gives us B2H6. That is our molecular formula. Ta-da! We did it! Okay, we've got 2 more examples that we're going to work through. Again, press pause, work at it, come back to me to check the answer. Chemical analysis indicates that a compound is 28.64% sulfur and 71.36% bromine. The molar mass of this unknown compound is 223.94 grams per mole. I want you to find the molecular formula. To do that, though, we have to do empirical formula first. And of course, we are assuming, do you have to write this every time? Yes. Yes, you do. So the mass of sulfur will be 28.64 grams, and the mass of bromine will be 71.36 grams. Find the amount of moles of each. Okay, here are molar amounts. Which one are we going to divide by? They are almost identical, but by a 1/10,000th margin. Sulfur has the lowest amount of moles. So I'll divide both of them by that, 0.8930. And that gives me a ratio of 1:1. So our empirical formula is SBR, 1:1. Okay, now we need to find molecular formula. So I'm going to find my scale factor. All right, X is the molar mass of molecular divided by molar mass of empirical, which, when I add the molar masses of sulfur and bromine together, is 111.97 grams per mole. So that'll be 223.94 grams per mole divided by 111.97 grams per mole, and I get a scale factor of 2. So X SBR is actually 2 SBR, so our molecular formula is S2BR2. And that problem is done. We're going to do one last one. Work through it on your own first, guys. Please, please. Actually, we're done. Sorry. Yep. Have we done 5 pages already? Check, 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 and check. Okay, we're actually going to be done. Great job. Once again, thanks for stopping by. For this lesson, go try, I've got an extra practice worksheet. Go try the textbook questions, and then our lesson tomorrow is a shorter one. It's also going to include a virtual lab. Pop into Zoom or post a question on the discussion board if you need it. Thanks, and we'll see you guys later.